Hello, my name is Bill Gillespie. I work with the Metrum Research Group, and over the next few hours, I hope to give you a brief introduction to Bayesian modeling using STAN. My intention here is, well, like I said, to give you a brief introduction to Bayesian modeling and the practical use of STAN for PKPD applications. The primary intended audience are pharmacometricians or PKPD scientists. I'm assuming that you have background in PKPD modeling, some familiarity and experience with nonlinear regression, mixed effects modeling, and the use of R or possibly S+. I also assume that you have some basic understanding of Bayesian principles. This brief online workshop is essentially a set of excerpts that I've taken from a course that we've done at Metrum, either as sort of a rapid one-day course or as a somewhat more extended two-day workshop that we entitled Getting Started with Bayesian PKPD Modeling Using STAN. I'm going to focus on how to construct STAN models and analyze data with them. And in particular, I plan to skip material that relates to the fundamentals of Bayesian inference, data analysis, and Bayesian computation. For that, I encourage you to read the first 7 chapters as well as chapters 10 through 12 of Bayesian data analysis. That's a text. Let me bring that up just to give you a picture here. So that's a text written by several authors you see here. Andrew Gelman is lead, as well as you can see several other well-known Bayesian statisticians. It's a particularly good introduction, and in particular it's a fairly pragmatic introduction to Bayesian data analysis. It spends much more time on sort of how do you, in a practical sense, analyze data using Bayesian methods, and rather than spending a great deal of time on theory. Anyway, I strongly recommend the book in its entirety, but in particular, I recommend you cover these particular introductory chapters. Let's head back to full screen. Just to give you an outline of where I'll go. Actually, the first couple main bullet points here I'm going to be largely skipping through because, as I said, I'm going to be skipping over the basics of Bayesian statistical inference, so we'll skip that. Again, I encourage you to, if you want to, you can read over the brief slides I have here, but again, I recommend reading the text. Also on computation, I'm going to skip over the basics. I'll just spend a little bit of time talking about something called Hamiltonian Monte Carlo simulation, which is the particular flavor of Markov chain Monte Carlo simulation that is used by STAN. And then we'll jump right into the basics of STAN. You know, what is it? How do you get it? How do you run it? And in particular, we're going to be running it using RSTAN, which is an R package that links to STAN and allows you to run STAN models directly from the R interface. We'll do an initial demo just using a simple linear regression model. We'll jump on to what I've labeled as the first hands-on example here, which is a simple nonlinear regression. Talk a bit about assessing convergence with MCMC methods, how we go about programming hierarchical models, in other words, models that we might call mixed effects or population models in STAN. Talk a little bit about prior distributions as well as how to construct truncated distributions within STAN, and then jump to our second hands-on example, which will be a nonlinear mixed effects model. Then we'll jump into user-defined functions and talk about programming for pharmacometricians, which will exercise what we learned about user-defined functions to construct PK models and how you deal with things like sequences of dosing and observation events in a schedule. And then that leads to our next example, which is a population PK example. And finally, we'll close out talking a bit about dealing with censored data in STAN and illustrate that in the case of dealing with BQL data in a population PK analysis. That's where we're heading. So let's get you set up. So at the site where you downloaded, or at the site where you link to this particular video, there is also a link there to download the course materials, which are contained in a zip file. So that contains the workshop materials. And when you unzip that downloaded file, the resulting directory contains a directory tree with this set of directories, one called data, deliv, doc, model, and script. And in fact, why don't I show you what that looks like? Here, we can get rid of this guy. Okay, here it is in my directory. So this is actually an example of the zip file. When you unzip that, you will get a folder like you see here. When we open that up, you see we have a set of folders or directories here by the names I just mentioned. First is kind of obvious. That's where we're going to be putting data. Deliv is where we're going to be writing a number of our analysis results, things like plots and tables that are generated when we do the data analyses. Doc contains a couple of useful things. In particular, excuse me, it contains a handout version of the slides that I'm using right now. In addition, I've got the Stan Modeling Language User's Guide is also available for you there. So we'll go ahead and close that for the time being. It's certainly a useful reference for, sorry, bring it up again. I encourage you to read through much of that after you've gone through the course. And you may want to refer to it now and then as you step through the course materials. Model is where we're going to put our Stan models, and script is where we have mostly our scripts and various supporting components within there. Okay, so and you'll notice, for example, when I open up script, you'll see several R scripts already there, which correspond to the examples we're going to do. Similarly, in model, you'll see the files containing the Stan model language code that we're also going to be using as part of that. Okay, back full screen. If you haven't already, please install R. You can download R from what's termed a CRAN site. I always forget what the acronym stands for, but it's related to the R project. In fact, you can actually, if you want, you can just click on this link right here. It'll take you there, download it, and install it for whatever system you're working on. And I recommend you install, in fact, you will need both RBase and RTools from that site. Go ahead and open the script directory from that directory tree I just showed you, and you'll see in there's a file called pkgsetup.r, and you're going to want to go ahead and open that up using your favorite R environment. Since so many people these days are using RStudio, that's the environment I'll use for our examples. Set the working directory to the script directory and run that package setup.r script. What that's going to do is that's going to download and install the R packages that are used in the examples that I'll be doing, as well as any dependencies for those R packages. And as I say here, be patient. It does take a while because what it'll be doing is it'll be downloading the source versions of those packages and compiling them. Okay, so let's start digging in. Okay, this is the section, as I say, I'm going to be skipping through, which is a very brief introduction to Bayesian statistical principles and methods. Certainly feel free to take a look at that. Skip right over that. Okay, so here's where it starts talking about posterior simulation, is where we start talking about Bayesian computation. Again, I encourage you to read about that in the Bayesian data analysis text. What I will start with, though, is let's talk a little bit about Hamiltonian Monte Carlo simulation, which is a particular approach for doing posterior simulation. By posterior simulation, I mean simulation from the posterior distribution from which we're going to be making inferences about our various model parameters and model predictions. And it's a particular flavor of Markov chain Monte Carlo simulation. And as we'll see here, it's one that offers some significant advantages over some of the more standard methods that are out there, but it also has its own limitations, so we'll touch on those. So to introduce Hamiltonian Monte Carlo simulation, let me start with sort of a physical analogy to motivate HMC, or Hamiltonian Monte Carlo simulation. And in classical mechanics, the Hamiltonian equations describe the evolution of a physical system over time. And the state of the system is described in terms of kinetic energy as a function of momentum, in other words, mass times velocity, and potential energy as a function of position. For the analogy, what we're going to do is equate the model parameters, which I'm often going to symbolize as theta to represent the vector of all model parameters. Let's equate that with position in our analogous physical system, and we're going to equate a set of auxiliary parameters that we're going to call rho. We're going to equate those to momentum. Now we're going to define a Hamiltonian in terms of the joint posterior distribution of theta and rho. So in particular, the Hamiltonian, which is a function of both theta and rho, is going to be minus the log of our joint posterior distribution right here. Since we're dealing, well, we can write that out in terms of we can break that up in terms of the posterior distribution for the parameters alone, as well as a distribution for the momentum parameters here, conditioned on both the other model parameters and the data. We can, take advantage of the properties of logs here, and we can write that out as a sum of those two components. And here I'm just changing notation here and describing those two components as either V or T, where V represents potential energy, which we describe in terms of minus the log of our posterior distribution of our parameters, and then our kinetic energy here, T, is minus the log of the posterior distribution of our momentum parameters. Now, keep in mind that theta is the thing we really care about. The rhos are auxiliary parameters that allow us to use Hamiltonian mechanics to more efficiently move through the relevant parts of the parameter space. But in a sense, other than the fact that they help that process, they're essentially nuisance parameters. Now, usually the distribution of rho is chosen to be independent of theta, just as a matter of convenience. And a typical example we show here then that the distribution of rho given theta, then if it's independent of theta, we can simply write that as the distribution of rho with no dependence on theta. And we often pick something convenient, something perhaps like a normal centered at 0 with some covariance matrix in here. So that's just a matter of convenience for our calculations. And now suppose that we place a frictionless particle on that potential energy surface. The potential energy, again, being minus the log of our posterior distribution of our model parameters. And let's suppose we place that frictionless particle at some position we'll call theta t minus 1. Then what we're going to do is we're going to give that particle a shove that imparts some momentum that we'll call rho t minus 1. And we're going to impart that momentum to that particle at time t minus 1. Now, when we do that, the particle is going to move over the surface according to Hamiltonian dynamics. And what we're going to do is then stop the particle at some pre-specified time t and measure its position. And we'll call that theta t. Now we're going to randomly sample a new momentum from our distribution of momentum and give the particle another shove, and do that over and over and over again, and in the process recording our sequence of positions for theta. Now, though the initial momentum at each step is random, the subsequent path is going to favor regions of lower potential energy or equivalently higher probability density, and the set of sampled positions turn out to be distributed according to the target posterior density. Now, in practice, the Hamiltonian equations are solved numerically, and as a result, some error gets introduced into the estimated path. So in the typical Hamiltonian Monte Carlo simulation methods, there's also a Metropolis step that is used to basically adjust for that numerical error and assure that the position samples ultimately converge in distribution to our target distribution, namely the posterior distribution of our model parameters. So, the point here is that by introducing these auxiliary momentum parameters in here, we're taking advantage of some additional knowledge we have about the distribution that we're working with. In particular, we're going to be taking advantage of some gradient information that allows us to recognize sort of what is the more optimal direction to be moving in as we try to describe our posterior distribution. And it turns out that in most cases that results in a much more efficient sampling of our posterior distribution than using the more random walk approaches like Gibbs sampling or Metropolis Hastings. Now, to get more specific about what the HMC algorithm is, what we do is repeat the following steps. We first sample some momentum here that we'll call rho t minus 1 from our normal 0 sigma distribution. Then we're going to simultaneously update both theta and rho by numerically solving the Hamiltonian equations using a numerical integration method called the leapfrog method to generate a proposal here that we're going to call theta star. And that proposal then is a proposal for theta t. And then we use a Metropolis step to decide whether or not to accept or reject that proposal as the theta t. If it's rejected, we just keep the previous theta t. If we accept it, we replace theta t with theta star. And then internal to this, we have our leapfrog method. So using our starting values, theta t minus 1 and rho t minus 1, the leapfrog method alternates these half-step updates of rho with full-step updates of theta using this particular numerical algorithm. It's loosely speaking, it's sort of similar to something like Euler's method. It's actually not much more complicated, but it turns out that in these kinds of settings, the leapfrog method results in lesser errors than does Euler's method. That's the use of the leapfrog method in this context. And then for each HMC iteration, you repeat these steps L times. In other words, you pre-specify what L is. So you repeat it L times to yield proposal values for theta star and rho star. So we're going to have proposals for both. At that point, you compute this ratio. You can see it's written here in terms of the Hamiltonian, both for the Hamiltonian at the starting point and at the proposal, which turns out to be a ratio of our probability densities here. You can see our probability density for theta star and for rho star and those are divided by the values at the starting point for that particular step. And then you have an accept reject step, which you accept theta star as theta t with probability equal to which is ever the minimum of r or 1. in here, and if it's rejected, then you simply substitute back your previous value of theta t into the current value of theta t. Now, since rho is sampled independently of theta and the previous values of rho, there's actually no value in keeping keeping the proposal at all, because at each given step we're just going to be sampling a new value from that normal distribution, so we don't have to worry about updating rho except in a simple independent sense. So that process again is going to be yielding a whole sequence of those theta t's, which then will converge in distribution to the posterior distribution that we're interested in getting. Now, if you noticed when we were talking about this, there were a few different parameters, tuning parameters in here. In fact, one I kind of skipped over when we were looking at the leapfrog method. There is a step size internal to that, this epsilon term right here. And in addition, recall that we said there were L. You're going to pre-specify the value of L. In addition, if we step back to in here, in our steps where we're sampling rho, we also have to specify this covariance matrix in here. So we've got those three elements that we have to tune in order to optimize the HMC algorithm, which is what I'm set. So we've got to set the discretization time, in other words, the epsilon, the number of leapfrog steps L, and what is termed the mass matrix, which is just the inverse of that covariance matrix. And sampling efficiency is very sensitive to all of those. As I say here, if epsilon is too large, you end up with too many of the proposals are being rejected, and that results in inefficiency. If epsilon is too small, you just end up with very long simulation times. So your leapfrog method gets very accurate, but the computational efficiency is poor. If L is too large, then you're doing too much work for each iteration. In other words, you're just doing way more steps than is particularly useful. On the other hand, if L is too small, the method devolves into essentially a random walk, which offers you no advantage over things like Gibbs sampling. Also, if our mass matrix is poorly tuned to the problem, then you have to try and adjust epsilon or L. In particular, epsilon would need to be decreased or L increased to maintain sufficient precision and efficiency. Finally, just comment that Stan attempts to automatically optimize those parameters using something called the NUTS algorithm, or the no U-turn sampling algorithm in here, and I won't be describing that in detail, but I do give a reference to a paper here that does describe that in some detail. So in most cases, we're not going to be spending time trying to adjust those ourselves. We'll be relying on Stan's built-in capabilities to optimize those parameters. Okay, so I believe our next step, oh no, sorry, I was jumping the gun. This is just a couple of slides illustrating the efficiency of Hamiltonian Monte Carlo versus other methods which tend to be characterized as more random walk approaches, such as Metropolis, Hastings, and Gibbs sampling. In this case, we're looking at, on the left-hand side, a random walk Metropolis sample. The example they've got here is they've actually got we're looking at really sort of one dimension of a 100-dimensional problem in here. So you can think of this as being like a model with 100 parameters, and we're looking at the sequence of sampled parameter values over a sequence of iterations here. And you can see here we've got a case here where we're looking at 1,000 iterations of a random walk Metropolis, and it's very slowly sort of meandering through the parameter space there. In particular, it looks like something less than entirely random. To make this worse, it actually, if you read in detail down here, is it comments that to match the computation time between these two approaches, 150 where am I going here? Yeah, 150 updates of the random walk was counted as a single iteration on this scale. So each of the samples in this actually represents 150 random walk steps. So so this 1,000 iterations corresponds to 150,000 iterations versus 1,000 iterations of the Hamiltonian Monte Carlo, in which you can see looks like a far more random and consistent exploration of the probability space that it's trying to explore. Now keep in mind also, though, that each Hamiltonian Monte Carlo iteration is much more expensive than each of the 150,000 iterations. So they chose this particular number, the 150,000 versus 1,000, in order to match up the computation time. So anyway, even when you do that, when you have an equal amount of computation time, it's much more efficient with the Hamiltonian Monte Carlo sampler. And this is a similar kind of picture from another article. Let's see, this is by Hoffman and Gelman. Well, this is one where they're actually exploring the no U-turn sampler, which adaptively adjusts the tuning parameters for the Hamiltonian Monte Carlo, but it compared Metropolis and Gibbs to nuts, and this is all compared in the one at the end here, which is a set of independent samples, which would be sort of the gold standard in this. And you can see the nuts and the independent samples seem to have described largely the same distribution, whereas the Gibbs and Metropolis samplers have yet to explore the entire probability range in here, and thus are far less efficient. Now, a couple issues here. Actually, kind of this is all sort of fallout from one particular issue with HMC, is that HMC requires calculation of the gradient. Here you can see it's the derivative of the log of the posterior with respect to the model parameters. And if we jump back real quick to our leapfrog method, you can see where this comes in, is here you've got the gradient on the right hand side of one of the leapfrog steps here. So in order to do Hamiltonian Monte Carlo, you have it be efficient, you have to be able to efficiently calculate that gradient. So that's one aspect. The other fallout from that is it turns out that Hamiltonian Monte Carlo is suitable only for sampling of continuous parameters. So you cannot sample discrete parameters. Now that's just to make sure that we're clear on what that means, is we're going to make a distinction between parameters and data. You can still model discrete data as long as the likelihood for that discrete data depends only on continuous parameters, which is by far the case in the large majority of situations. But if you do have models with discrete parameters, for example, finite mixture models of different kinds, that cannot be done directly. In many cases, you can implement them by what they term marginalizing out the discrete parameters, but it is an additional step that would need to be implemented to be able to use HMC and in particular to use STAN. So finally, let's get to the specific of STAN. Well, first of all, what is it? Well, as its term here, as I say here, STAN is a general purpose Bayesian modeling package. It's got a very general model specification language. It primarily uses a Hamiltonian Monte Carlo sampler, either standard HMC or the NUTS algorithm. In addition, it does implement a couple other methods. It has a tool in there for optimization that can be used to estimate posterior modes. There's also something called a variational inference method for approximate Bayesian inference. The variational inference method is labeled at this point still as experimental. It's one of those things that for certain problems it works very well. For others it can introduce a degree, an unacceptable degree of bias, and it's not always real easy to distinguish which cases are which. So I would say it's kind of a use at your own risk methodology at this point. STAN is developed by a team headed by Andrew Gelman at Columbia University. At its core, STAN is a C++ program. That's available with several interfaces. There's the RSTAN interface that we'll be using today, but there's also interfaces for Python. It's called PyStan. CommandStan is a command line interface to STAN, where you use it directly from your operating system interface. There's one for MATLAB, for Julia, and for Stata. Shiny STAN that I listed here actually isn't a STAN interface. It's actually it's a tool for diagnosing sampling problems and things like that from STAN. Let's see, what did I want to show you here? Let me show you, well, let's actually take a look at the website here. Let me go ahead and bring this up. Actually, I don't want to do it from, where did it, oh, I see what I did. This is the main website for STAN. So it gives a few things talking about getting started and so on. If you go, there's a click on the thing for interfaces, you'll see the various interfaces listed with links to get to them. Documents of various kinds are listed, but in particular there's the main user's guide, which I've also provided in the materials that you downloaded. Let's see, let me point to community here. There is a users group and a developers group. I'd certainly recommend you start with the users forum. I'll just go ahead and click on that. That uses Discourse as the platform for that, so you can use that as a place where you can ask questions or answer them for various folks.